Hi, I'm Dave Adamson from GSI Environmental.
And I'm Chuck Newell, also from GSI Environmental. This is one of a series of short videos that highlights cutting-edge CERTUP and ESTCP projects.
Okay, well today we're going to talk about a new generation of techniques for collecting soil cores that are designed to get better data from the subsurface.
Now here are some key points about this project. First-generation site characterization methods using monitoring wells and soil samples collected in jars have problems with missing data. Second-generation methods based on high-resolution characterization tools, it's a great improvement for understanding heterogeneity, matrix diffusion, and mass flux, but they still have problems in the collection and preservation of soil samples.
But there are a class of relatively new third-generation site characterization methods that can give us better data. And one really promising approach is cryogenic core collection, also called C3. C3 freezes soil samples from the subsurface cores to limit losses of key liquids and gases and preserves the core in the way that was found in the subsurface.
Then a high-throughput laboratory analysis of the frozen cores is performed, providing a larger amount of data that represents more accurately the in-situ conditions than data, say, generated from field processing of unfrozen cores.
And now this technique was developed and optimized over the last decade through several CERTUP and ESTCP projects. Chuck, how about you put on your historian's hat and give us a short tour of the history?
Sure. Now, the work started with Dr. Rick Johnson's CERTUP project ER 1559 back in 2007, where the idea of cryogenic core was tested out first in the lab and then in the field. The idea proved feasible and easy to integrate into routine field sampling. Then CERTUP project ER 1740 followed and built upon these preliminary positive experiments with more development work in the field and the lab. Then this CERTUP project led to ESTCP project ER 2015-87, where further enhancement and testing was performed at a remediation site. The research team relied upon cryogenic core collection as a major site investigation tool to better understand the actual performance of remediation technology in the source zone and evaluate if rebound of groundwater concentrations might occur in the future.
Okay, so we've got this series of projects. Today we're going to focus on one of the projects, ER 1740. It was called a State of the Science Review of Management of Contaminants Stored in Low Permeability Zones. The CERTUP project, it was led by Dr. Tom Sale from Colorado State University, along with PIs Dr. Rick Johnson from Oregon Health and Science University and Mr. Rick Rogers, Drilling Engineers Incorporated.
Now, Dave, the term cryogenic coring implies in-situ freezing. So does that basically mean what we're doing is to pull a popsicle out of the subsurface and thaw it out for more information?
Great analogy to start. Maybe a little bit more technically complex than that.
Okay, well, let's get into the technical nuts and bolts of the cryogenic coring. How about you start with a problem statement from this CERTUP project?
Okay, the researchers had a vision to improve the way we collect data from the subsurface. As many practitioners in the remediation industry know, what we're typically doing is grabbing samples from monitoring wells and soil cores. We refer to these generally as first-generation site characterization methods. There are more advanced techniques, which we might call second-generation characterization methods. That's things like the membrane interface probe, MIP, Waterloo profiler, and hydraulic profiling tool. However, these first and second generation methods, they do have some limitations as well.
For example, 1G monitoring well methods only capture the water from transmissive zones, and the water sample is often a mixture of water from different depths, causing mistakes in characterizing the plume structure, and it results in a conceptual model that may not be accurate. On the soil side, collecting soil samples from exposed cores are subject to loss of volatile compounds. You lose the soil structure, and sometimes you miss the NAPL.
And the 2G tools, they're better, but they still have some difficulties in characterizing sorbed phase or NAPL in soil, and often some of the core sample isn't captured and it's lost.
Okay, Dave, well, if we're trying to solve an engineering problem or find a better solution, sometimes you want to assume what is the ideal situation, the ideal solution. So here's a question for you, Dave. In a perfect world, what do you think a site characterization sampler should be capable of doing?
Good question, Chuck. The simple answer is that a good sampler should tell us exactly what the subsurface soil and groundwater looks like. More specifically, you want to have a good recovery of the core, meaning that the length of the collected core should be as close to the depth which the sample tube is advanced as possible. Example of a less than satisfactory recovery is the occurrence when you're in maybe flowing sands in saturated media, which means that the loose sand falling off the core is causing a lower pressure than the adjacent formation. And that in turn is going to push sand outside of the borehole into the core sample, making it pretty hard to identify the formation and the plume structure. And that's shown in the graphic here.
Well, that makes sense. So desirable attribute number one, good core recovery. Anything else?
Well, you'd also hope for a good preservation. You're taking the core sample out of the ground, but that's really just the first and sort of superficial step of site characterization. We also have to take that core back to the lab and analyze it inch by inch to find out some things about the soil properties, like the porosity, the clay content, also what compounds are present, what concentrations, and what form. Are they reduced or oxidized? Then you've got pore water or NAPL or sorbed compounds, other things to worry about. Maybe you're also interested in the microbial ecology. But if you're cutting that core open and putting it into soil jars, then you've got the opportunity for bad things to happen. The air can cause redox conditions in the core to change. Gases can be lost. Microorganisms can die. And maybe you're losing NAPL or water. So basically, we want everything within that core to remain in a pristine state on its way to the lab, and good sample preservation is the key to that.
Okay, so that's desirable attribute number 2, good preservation. The good news is that this third-generation cryogenic core collection technique, developed and tested in this CERTA project, is proven to greatly improve the recovery and improve the core preservation for the trip back to the lab. So in other words, it's 2 for 2 on our wish list.
All right. Well, let's see how it works.
Well, first, I want to note at this point the cryogenic coring research team has gone out to multiple field locations, and they've tested different assemblies of samplers and protocols prior to finalizing 2 different C3 systems.
The team was modifying conventional hollow stem auger to allow liquid nitrogen, that's the freezing agent, to flow down around the core to freeze it. They modified the drive shoe to allow the use of sample liners with a 2.5-inch outer diameter so that there's sufficient clearance in the core barrel for the cooling assembly and the insulation.
So moreover, the liquid nitrogen pressure, the proper diameter of the cooling tube and cooling coil, that's where that liquid nitrogen travels, the feasible length of the core sample, options for insulation between the barrel and the cooling coil, material for the sample liners, and many other important parameters were tested as part of this research.
And then the researchers were also evaluating things like improving the recovery, as we were discussing earlier, controlling flowing sands from mixing with the sample. They want to have a short enough freezing time, but not requiring too large of a liquid nitrogen supply. They want to reduce the probability of downhole ice locking. So these are all factors that they're trying to weigh in that final design.
So quite a list of things have been evaluated. So let's show this final design, which is really 2 different parts.
All right.
So 2 different systems were recommended for in situ freezing of the sample core. But the critical features of both systems included, number 1, extending the cooling system into the drive shoe without insulation, which improved freezing at the front of the core and also reduced the effects of flowing sands by freezing ahead of the drive shoe. And feature number 2 is adding insulation around the reaming sections of the cooling coils in the cylinder, and that's critical for rapid freezing and limited downhole ice locking.
And the best cooling agent turned out to be liquid nitrogen. It has a low exhaust temperature. It's got sufficient cooling capacity for a full day's worth of coring. It's also reasonably priced and widely available.
Now, the delivery of that liquid nitrogen is the key to successful in situ freezing. Here's a list of steps serving as a guideline that you potential popsicle makers out there need to follow.
We've got a nice video here. It was recorded by drilling engineers to give a good practical perspective.
Cryogenic coring is an exciting new way to collect samples of soils from the subsurface settings. Has advantages with respect to controlling flowing sands and recovery and preservation of samples. The cryogenic core collection involves advancing the hollow stem auger and the C3 barrel, filling the barrel with a sample, injection of liquid nitrogen through the C3 system to freeze the core, and the formation immediately below the drive shoe, withdrawal of the cryogenic core collection system and sample from the hole, and finally the hollow stem auger and the C3 barrel are advanced for the next sample interval. Collected cores are placed on dry ice in the field and shipped to a laboratory for analysis. Cryogenic coring is going to be a big part of our future of collecting subsurface soil samples.
Looks like an easy step-by-step process.
All right, let's look at the metrics they were using to assess performance of the cryogenic coring technology. They ended up with excellent recovery. At one test site, they got close to 100%. At another site, 85% compared to less than 15% without freezing. The time to freeze was drastically shortened after optimizing the cooling coils, that's shown in the figure here, where the red optimized system lowered the temperature from 33 to negative 30 degrees in just about 10 minutes or so.
And also, there was no downhole ice locking encountered during the field work.
Okay, so once you've got the cores to the depth you've specified in your work plan, you put the cores on dry ice in the cooler and ship them back to the lab for analysis.
So you end up with a cooler full of these frozen cores with all that key, hard-to-get information just sitting there ready for the lab work. That's pretty awesome.
Yeah. So let's take a look at how the hidden data is revealed, the analysis of the core samples.
Sure. Now, the parameters that the project team was interested in, and all site investigators are interested in, include the contaminants, dissolved gases, redox conditions, mineralogy, microbial ecology, and the hydraulic properties. Quite a comprehensive analysis.
That's right, but remember how these samples are in these frozen 2.5-foot cores, so the processing of the samples is really important. And the figures show us the tools and equipment the researchers used in their core processing. Got a cutoff saw, a chisel and hammer to cut the frozen core, sort of like the tools a surgeon uses in the operating room to cut through solid bones. Figure B is a stop block that can quickly gauge the length of the frozen core for each cut. All this processing was performed in a fume hood.
Now see that the researcher in the photo has proper safety gear, including these noise-canceling headphones. Good job in the safety plan. Now he's cutting the cores into smaller cylindrical discs using that cutoff saw shown here on the left. In general, a 1-inch thick disc was collected every 4 inches of the core. You can see a typical sampling pattern in this diagram here, based on where you get 7 1-inch thick sample discs, A through G. Note that everything was done as fast as possible to minimize the thawing of the core.
And each of these 1-inch discs, you're putting them into a splitting device shown here. The researcher then uses a hammer and chisel to split it into 3 pieces for different analyses, according to the pattern shown on the right. Let's take a look then at the data collected from these cryogenic cores for 3 different holes drilled to install monitoring wells.
Now, the best way to see what you get is to look at the concentrations of the chemical compounds along with the geologic cross-sections. So here we go. The first data figure shows what's going on in monitoring well MW38C at one of the field sites. The inset here includes the legend for the cross-section. The key points are, number 1, TCE was detected in low concentration overall, and no methane was detected at all. And number 2, there didn't appear to be a clear correlation at this site between TCE and the soil type. Not very exciting. But one point of interest is that the redox, reduction oxidation potential in this well was higher than those at 2 nearby wells.
Okay, so here are the results from another monitoring well, MW173F. In this well, TCE was detected at a higher concentration. Methane was also observed in the transmissive zones, and this is related to the injection of lactate near the well in the late 2000s. Now, if we look again at the TCE concentrations, we notice that TCE was generally lower in the transmissive zones compared to the low K zones. And this observation is really reflecting preferential delivery of lactate to the transmissive zones for treatment.
Now, the last figure shows the characterization results of well 700C. The geologic log here was less complex than the previous 2 wells, with a continuous transmissive zone at around 14 to 17 feet below ground surface. Now, within this transmissive zone, we observed high concentrations of TCE, while high concentrations of methanes were seen in the low permeability, that low K zone. These observations revealed an inverse correlation between methane and TCE, suggesting an active ongoing treatment was occurring in that low permeability zones.
So the next graphic then shows the microbial results associated with this well. And so we see high levels of 16S rRNA genes detected in the low K zone, and this serves as another line of evidence for the active treatment. Another important finding based on these results is that the low K zones were potentially acting as a diffusive reactive sink for TCE.
So the 3G method proved to provide much more detailed and more reliable data than the conventional methods, especially the depth-specific concentrations and the ability to relate these chemical analytical results to geologic logging results. The overall analytical process, however, is somewhat labor-intensive, and these nicely frozen popsicle-like cores do get destroyed when they're analyzed. Dave, if there's only some way of, say, X-raying the core to get this important information without having to cut it all up, that would be really neat.
Well, that's a good idea, Chuck. You know, the project team actually did test several frozen core scanning methods on lab-synthesized cores to find out what their alternatives might be. In this case, the idea was to identify the compositions within the core, meaning the locations of the major phases, air, water, soil, and NAPL, and then use these compositional data to guide the subsampling process.
Well, cool. What'd they find out?
Well, here are some of the potential options. Notice that these are all candidate technologies, but they're actually medical scanning methods. And their results showed that magnetic resonance imaging, or MRI, was probably the best potential candidate for sensitive NAPL detection in the frozen core samples.
Oh, really interesting. Well, now let's go through the key points once again before concluding today's short video.
Sure. First, the first generation site characterization methods, conventional monitoring wells and subsurface grab samples, as well as the second generation methods, they have problems in terms of the bias towards highly transmissive zones, their limitations in the preservation of pore fluids, volatile compounds, redox conditions, and so forth. The research team said we can do better if we freeze soil samples in the subsurface.
Now, this is called Cryogenic Core Collection, or C3, and it utilizes in situ freezing to limit losses of core from sampling tubes and to preserve pore fluids, including water, non-aqueous phase liquids, and gases.
And finally, a lab-based system that they developed allowed high-throughput analysis of frozen cores, provided a larger amount of data that represents more accurately those in situ conditions than the data generated from field processing of unfrozen cores.
Well, that concludes the short video. I'd like to direct our audience to the CERTUP ESTCP website at certup-estcp.org to see project reports and other resources. And remember, this is just one of a number of CERTUP and ESTCP project summaries here and on the CERTUP ESTCP channel. Just go to YouTube and search for CERTUP ESTCP micro lectures to see more of these short, focused graphical project summaries of these great projects.